previous video, we just saw our first type of discontinuity, which is a removable discontinuity, which we said wasn't too bad. In this video, we're going to talk about now jump discontinuities. So these are going to be, in some sense, worse than the previous ones, the removable discontinuity. Just as before, let's just start off with a couple of drawings of what this looks like. So this is a function that has a jump discontinuity at c. A couple others that would look like this might be something like this. And so the point here is that in these functions, you have the phenomenon. So take a look here, see if you can express in your own words what's going on here. What's going on is that the limit from the left as f of x goes to c, as x goes to c of f of x exists. The limit from the right as f of x, as x goes to c of f of x exists. But those two limits don't equal. So the left-hand limit and the right-hand limit both exist, but don't equal. So here we have the limit as x goes to c from the left. This exists. The limit as x goes to c from the right of f of x exists. But these don't equal. And because they don't equal, this means that the overall limit as x goes to c of f of x does not exist. So recall back from one of our previous slides that's saying here that there were three things that you had to have happen for f to be continuous at a given point. Here we're violating the fact that this limit exists. So in the removal discontinuity, we either had f of c to be not defined, or we had f of c to be defined, this limit to exist, but they weren't equal. Now this limit doesn't exist because even though the two one-sided limits exist, even though the two one-sided limit exists, the overall limit doesn't exist. So this is a worse version of the removable discontinuity. We can't just plop in a point here to make it continuous. It would take much more work, much more changes to our function in order to make it continuous. However, we should note here, take a look at these two pictures. I guess I call the first one f of x, let's call the second one g of x. Think for yourself, this was classic asking somebody which one seems nicer comparatively speaking than the others. And hopefully somebody would tell me that f of x is nicer than g of x because the value of f of x at c at least matches this right-hand limit here, while the value of g of c matches neither the right-hand limit nor the left-hand limit. So this is suggestive. Whenever we notice this kind of some property like that, we should think about how to turn that into a definition. And so what we have is the definition of one-sided continuity. And so for one-sided continuity, so we're going to have left continuous and right continuous. So a function f is called, so our first one is going to be left continuous at x is equal to c if the limit from the left of f of x is equal to f of c. And then we should have a corresponding right continuous at x is equal to c. Well, so this would be if the limit from the right of f of x was equal to f of c. And so in the picture that we see before here, using this new definition, the limit from the right equals f of c here. So this is right continuous but not left continuous. This is neither left nor right continuous. So examples here. So this is left continuous, and this is right continuous. And so then just note here that think about what happens to a function is both left and right continuous at a single point. And that actually is going to exactly be the same condition as the function just being continuous. So left continuous and right continuous is equivalent to just saying continuous. For all of these, I guess I should be saying at C, at some point C. Okay, so these are our definitions. Let's think about some functions here and that have these jump discontinuities. So one example that we've thought about already in the past was the function where f of x is the absolute value of x over x. So this function we saw ends up looking like this. So it has a jump discontinuity. How about another one? So then here's going to be a piecewise defined function. So we'll say that d of x is equal to x3 or x, where it's equal to x if x is strictly less than 1. It's equal to 3 if x is between 1 and 3 inclusive, and it's equal to x for x is strictly bigger than 3. Drawing this out, 1, 2, 3, 4, 1, 2, 3, 4. So that should be a hole there because it's this part of it is only defined for x strictly less than 1. For x between 1 and 3, it looks like that. For x is bigger than 3, it looks like that. So that's a hole. Sorry for if that's a little bit sloppy here. But we can see that right here, at x is equal to 1, we have a jump discontinuity. But we see also that the function is actually, it is right continuous at x is equal to 1. Everywhere else the function is continuous. It's continuous, so we know that x is continuous. So everything down here is continuous. We know the function 3 is continuous, so it's continuous in between here. Everything greater than 3, x is again going to be continuous. So the only tricky spot would be what happens at x is equal to 3. But fortunately, the limit from the left equals the limit from the right equals the function value there. So this is continuous. And so this is our second type of discontinuity.